It's more like I sometimes like back up to Steve because he knows it.
Yeah.
I think we'll start, I guess. We are privileged to have a talk from Mr. Colin McClarty, who received his education at Case Western and continues to teach as the Truman P. Handy Professor of Intellectual Philosophy. I believe it's on how to prove X, if I'm not mistaken. So, without further ado, I'll let him take it away.
Well, it's on what does it take to prove X. It's not how to prove in the sense of how to find the proof, but what will you need in that proof. And I want to watch how the question of what it takes to give a proof at all became the question of what it takes to prove some given result. And David Hilbert is the pivotal figure here. I want to stress Hilbert's insight in logic from the 1890s and on. Hilbert was He really saw this very well. He works in foundations of geometry and foundations of arithmetic for decades. And as Poincaré puts it, in the 1890s, he lectures on foundations of geometry, and he eventually publishes a book in 1897 for the first time, I think, called Foundations of Geometry. You can go and it's these groups of axioms, and he deduces all the theorems from the axioms. The point is this is supposed to be correct, unlike Euclid's elements, which are not really rigorous. Over and over in Euclid, you have some conclusion that you can't see exactly how it followed from the axioms as stated. Hilbert's goal was that you should be able to see exactly how each theorem follows, and then you should be able to show that each axiom group is actually needed. How do you show that an axiom is needed? Well, what you want to know is that if you take these axioms away, there's some other interpretation that would make them false. And so you're not going to get them without posing them as axioms. There's some other interpretation of the other axioms. The famous one to us now is the parallel postulate. How do you know you need the parallel postulate? Well, because if you can give a model of all the axioms except the parallel postulate, say the hyperbolic plane model, that satisfies all the other axioms and not this. So that is, say, you're not going to be able to use this from the other axioms. Hilbert was not the only person working on this, but he was the best. And Henri Poincaré says of Hilbert, one could confine Hilbert's axioms to a reasoning machine, such as the logical piano of Jevons, and one would see all of geometry come out. These axioms are adequate in the sense that you don't have to understand them. You certainly don't need to know what's the idea behind them. A machine that can take premises and give conclusions could take these axioms and derive all of geometry. Now, Poincaré is entirely wrong about this. He's wrong in every way. Jevons' machine only evaluates syllogisms. It cannot handle reasoning, for every x there exists a y. It's not even close to that. Excuse me. And Hilbert's axioms are not that rigorous by modern standards. Today, people will say over and over again, some term here is not well enough defined, it's not that rigorous. But Poincaré is ahead of Hilbert in one way. Confined it to a reasoning machine. Hilbert would not have said this, but he should have. Hilbert couldn't have expressed his goal that clearly, but Poincaré spoke well to this point. That really is the right way to understand what Hilbert was aiming for. I mean, if you want to be historically sensitive, you have to know what it is to aim for a goal that you can't yet state clearly. But if you want a clear statement, that's the one. These axioms should be so thorough that a machine can reason from them. And Hilbert did that. And he developed this goal over time. By the 1930s, he still doesn't think in terms of machines because, of course, you don't have reasoning machines yet. But he becomes more and more clear that that's the point. These axioms should be mechanically interpretable in the sense of not requiring any understanding. You just crank and it comes out. I'm not going to linger on his philosophy of formalism. Hilbert is famous for having a philosophy of formalism. He doesn't use the term. Hilbert comes up with a philosophy of mathematics where mathematics should all be about formulas. And the study of these formulas should be entirely finite. These formulas are finite objects. We should be able to retain all of mathematics, and as he says in this, no one will be able to drive us from the paradise Cantor has made for us. He's an early adopter of Cantor's set theory, this theory of transfinite sets. A lot of people, still at the time Hilbert wrote this, are suspicious of Cantor's set theory. How do we know it's true? Can we really talk about infinite sets? And Hilbert's whole point is to say, we don't need to ask if it's true. The question, can we really talk about these, means, can we manipulate formulas that we think of as dealing with these? That's formalism, but that's not his term for it. The term formalism comes from Frege and Brouwer, and is a complicated history. What Hilbert does say, though, in 1900, when he's giving his Paris talk, when he's laying out the famous Hilbert problems, he's been invited to give a talk at the Second International Congress of Mathematicians. He sees that this talk should make him the leading figure in mathematics. His friend Minkowski writes to him and says it's going to make him the leading figure in mathematics. And he wants to do that. And so he presents, actually I believe in Paris he talked about 10 problems, but he circulated a list of 23 problems. Now somebody's found in manuscript the 24th problem. But the point of these 23 problems, these are to be problems that might guide 20th century mathematics. These problems, they should be important, they should be feasible. They should be problems whose solution will lead to more problems and more solutions. And the third problem is consistency of arithmetic. People are beginning to axiomatize arithmetic formally, and he wants to prove the consistency. In investigating the foundations of a science, and the one he's interested in is mathematics, we must set up a system of axioms. But above all, I wish to designate the following as the most important among the numerous questions which can be asked with regard to the axioms to prove that they're not contradictory. In his Foundations for Geometry, he gives these axioms, and he proves they're not contradictory in the way you might expect. He assumes the real numbers are there, and he shows that with real coordinates you can model all the axioms. You can define what a straight line is in just a solution to a linear equation. You can define what a circle is. And then you can show that in the real number plane, all of these axioms are true. So the axioms must be consistent. And he shows that, that if these axioms are consistent, then you can take away the parallel postulate and you can change it and say no two lines are parallel, any two lines meet. And you can find a model for that, again, using analysis on the real numbers. And also the one that says there, for a line, they're pointing out that there's many lines that don't meet this one. The hyperbolic geometry, where there's many. So he succeeds in showing geometry is not consistent by using real analysis. Light analysis, not what they would do in a real analysis course, but analysis on real numbers. But he sees that this isn't going to work for analysis itself. How do you know analysis is consistent? Well, you know analysis is consistent because you can define the terms in arithmetic using some set theory. And these issues are only becoming clear to people, what all's involved. But he quickly decides that simply proving consistency of arithmetic is going to be a key question. If we can do that, then we'll know how these things are done. But he wants to prove the consistency of arithmetic, not assuming some other thing, not assuming someplace else to interpret it, but from the ground up. And how is he going to do that? Because consistency in a formal system is a question about finite strings of symbols. This is true in set theory, it's true in any formal system. What we need to know is you can't write a sequence of formulas of arithmetic that ends with 0 equals 1, where each of these is either an axiom or follows from previous ones. I'll write MP for mode exponents. You might think could be your rule of inference. Consistency simply says there's no string of formulas where each is an axiom or follows from earlier ones, and the last one is 0 equals 1. Because, of course, we do prove that 0 is not equal to 1. So, and Hilbert says, look, these questions are easy. Finite strings? You might have worried about the transfinite numbers in contrast set theory. You might have worried that the continuum, we know it to be larger than the set of naturals. We don't know how much larger it is. We might like if it was the next size up, but we don't know. And you might worry, where do we talk about things, how do we get off talking about things this size? But you can't worry, how do we talk about finite strings of symbols? That's easy. Well, if not easy, at least doable. This is something we should be able to do. And Hilbert declares that we can. We can give a consistency proof for arithmetic using assumptions much weaker than arithmetic. Today we modernize this. He said we can show that assumptions much weaker than Peano arithmetic will suffice to prove set theory is consistent because it's just a matter of finite symbol strings. Now this is wrong. This was a mistake. You can't do this. But he thought you could do it. And it's a great mistake. A truly great mistake. It took a real genius to think we should be able to organize the study of symbol strings, and we should be able to give these consistency proofs. This should be, it won't convince us that the set that contrast transfinite sets exist, but we don't care if they exist. It will prove they can't lead to contradiction. And Gödel in 1931 proves no plausibly comprehensive axioms for mathematics suffice for their own consistency. We sometimes hear, Gödel's theorem says that Peano arithmetic can't prove its own consistency. And it's true as far as it goes. But of course, no one would be impressed if Peano arithmetic did prove its own consistency. That wouldn't convince anybody who doubted. Because it's already trivially apparent that if Peano arithmetic is not consistent, it will prove it is. Because it will prove everything. If Peano arithmetic is inconsistent, it will prove that such strings don't exist. And will simultaneously prove that they do. That's inconsistency. Well, it's inconsistency today. Now, with the kind of formal logic that we have and that Hilbert was already supporting, inconsistency was the same as proving everything. And then, of course, we have serious people working on paraconsistent logics and everything. But for Hilbert was saying, Gödel shows this is a stunning result. He describes it as applying to Principia Mathematica and related systems. Verwandte Systeme. Well, of course, you can't describe it the way we do now because the vocabulary we use now was invented to figure out what he was saying. But no plausibly comprehensive axioms. That is, axioms rich enough to do just the arithmetic you need to talk about finite symbol strings. At the time, of course, people had a lot of trouble understanding how could you interpret a string of symbols as a number. Right into the 1950s and 1960s, people were trying to explain how this idea of Gödel's that you could interpret a string of symbols by a number. Into the 1990s, people were writing books as if this was a problem. But everything you put on your computer is interpreted as a string of numbers. This is not the hard part anymore. But once you have enough arithmetic to manipulate these strings of numbers just a little bit, if your axioms have enough arithmetic to do that, they will not succeed at proving their own consistency. And again, that's not exactly the take-home message. The take-home message is certainly nothing simpler than that will. Because if they prove their own consistency, you wouldn't be impressed. But this means no fragment of them will either. Hilbert, remember, was hoping to get some leverage. The assumptions much weaker than Power arithmetic should suffice to prove set theory consistent. And here he's saying, no, all of Power arithmetic won't suffice to prove Power arithmetic is consistent. All of set theory, whatever set theory you take, won't suffice to prove that set theory is consistent. Today we focus this on Power arithmetic, but precisely Gödel's argument shows there's no decisive locus for consistency proofs. If Power arithmetic was consistent, it was complete. If it was complete, then we could say, it's where you should prove all consistency results, because they'd all be statements about numbers, and they'd all be provable there. It's not complete. No plausible foundation is complete, which means there's no one place to ask where anything gets proved. Could arithmetic possibly be inconsistent? What would it mean? Can we take this seriously, that arithmetic could be inconsistent? Well, the question only arises for formalized arithmetic. And this in two senses. If you mean the part of arithmetic that my brother knows, smart guy doesn't do logic, it's not a precise question. I don't know what arithmetic he knows. He doesn't know what arithmetic he knows. It's not a precise question, and whether it's inconsistent, well, I don't know what it is even. But it arises for formalized arithmetic, because when we formalize arithmetic, when we formalize, say, Peano arithmetic, we give an axiom scheme of induction for any formula phi x in the language. We've got this axiom. So we've got infinitely many axioms. Let's see, let phi of n be this statement. The sum of the numbers from 1 to n of that number is n times, I always forget this, n plus 1 over 2. So there's a statement you make about n. For any n, I can make this statement. And the axiom says, if 0 has that property, and anything you take, if it has that property, then so does its successor. If you know those two things, then you can conclude that everything has that property. But we need this for every statement phi n. Here I've written an equal sign, which I should not have written as an equal sign. I mean, that's a name for this formula. And we simply take this, for each formula, we have an axiom. We have infinitely many axioms. You can prove that no finite subset of them will suffice. Lots of them can be removed in favor of other ones. Any number of them can be removed for other ones, but you can't cut it down to finitely many. It would be a bold claim to say that you have grasped the expressive power of general formulas in the language of arithmetic. To claim that you understand every statement that can be made about a number? No. No. When you pursue this subject, you find that we very rarely make statements in arithmetic that involve more than a couple of quantifier changes for every x there exists a y such for every w. We really don't stack those very deep at all, commonly. Of course, there are results that depend on stacking them arbitrarily high, but not very often. So, we do claim to understand it in some sense. But I hope you see it's a lot to claim. It's a lot to claim. And this is a point that I owe to John Mayberry at Bristol. I don't know, he may have gotten it from someone else. We've only ever applied induction for conditions that make sense. It's one thing to say, we've only ever tested finitely many of these conditions. Well, that's kind of obvious because we've only been around a finite amount of time. We've only tested finitely many. You say, well, that's 0% of them. But that's not the most important thing. The most important thing is we only do inductions on properties we understand. If the formalism conceals an inconsistency, we should expect it to lie in conditions with no apparent sense. We should expect, it's not to be expected that some condition, somebody will someday find an inconsistency in arithmetic that was sort of simple and obvious and just waiting and nobody spotted it. So I think it's worth being modest and saying, we don't really know that Pownell arithmetic is consistent. This is it's a precisely axiomatized theory. It's got infinitely many axioms. These axioms get infinitely complex. And our experience is of using ones that make sense to us that we know what to do with. I do believe Pownell arithmetic is consistent. It's consistent. No, it just is. But it's worth noticing that this is not a banal claim. We're claiming to have insight into a really considerable thing when we say that. Now, set theory, any reasonable variant, does prove Pownell arithmetic is consistent. Gödel doesn't say there's no proofs of consistency of arithmetic. There's no proof of consistency of PA and PA. Set theory proves PA is consistent. For that matter, the theory PA plus a new axiom, PA is consistent, implies that PA is consistent. It's not hard to find theories that prove PA is consistent. But I think Kreisel gives the right interpretation of Gödel's theorem. It's an empirical claim. Between Gödel and our experience since then has shown you cannot prove consistency of PA from any assumptions more plausible than PA. That more or less is just a typo. I had a double negation. I mean, a deliberate double negation. Not less than not, and I only eliminated part of it. We cannot prove consistency of PA from any assumptions that are more plausible than PA itself. In other words, I'll put this on the board. We cannot prove con PA. See, now we're logicians. Con PA. Because we already know it. That is, just your familiarity with PA, you look at it, you say, these axioms make sense, they're true, is a more compelling argument than any consistency proof that can be given. Various consistency proofs that are given from various assumptions would have variously illuminating aspects to them. What they don't do is make you more certain of the consistency of PA than you were before. Before Gödel's theorem, if somebody said, you might be suspicious of set theory, but it can prove its own consistency, you'd have said, well, I'm still suspicious. But since Gödel, we can say more. If a set theory can prove its own consistency, it's not consistent. Since Gödel. And in fact, there was a famous case of this. Willard Quine proposed a set theory in the late 40s, which proved its own consistency. How long, I think, remarked that it could define truth in itself and so prove its own consistency. And so Quine had to go back and revise the theory. And in this way, I think Gödel's theorem makes me more persuaded of the consistency of Pownell arithmetic than I was before, Gödel's theorem and things like it. Because, for example, we show Pownell arithmetic does prove consistency of every finite fragment of it. For any finite fragment of PA proves consistency of that fragment. And it does this without also proving its own consistency. You see, you're sort of walking up to the edge when you prove this result. I've proved it for every finite fragment. Wait a minute, doesn't that mean the whole thing is consistent? No, my proof didn't go there. You say, good. That is, I was able to skirt disaster and skirt it. That convinces me that PA is consistent, more than I would. That's what increases my belief in consistency. That even when you press the limits, they hold. It doesn't prove one thing or another. And the same, we can't prove consistency of any foundation from any assumptions more plausible than that foundation was itself. So there are two responses you can have to Gödel's incompleteness theorem. You could give up on foundations. You say, well, we can't know they're consistent. Or you can keep track of what foundations work for what theorem. What Gödel has established, there's no one foundation. There's no pivot point that can handle all the questions about all the other foundations. No foundation can even handle its own consistency question, let alone everything. So keep track of what foundations work for what theorem. Now, I don't mean every mathematician should at every moment be asking, yes?
So I have a question.
Yes.
So you just made me very paranoid, but you said, in order to improve the consistency of any definite fragment.
Any finite fragment, yeah.
Any finite fragment.
Yeah.
But of course, if the arithmetic were inconsistent, it would do that.
Yeah.
So
Yeah.
why are you,
What I like about that is when you follow the proof, it doesn't take you the extra step to consistency of the whole thing. It very naturally cuts off short of consistency of the whole thing.
So this is giving you that's why it gives you some confidence.
Yeah, I say it's like skirting the edge.
If the proof generalized to prove all consistency of all of PA, then you'd be worried.
Then the consistency would then be refuted by Gödel's argument. If it did prove its consistency, that would be a disaster.
Yes, okay, very good. Very good.
And I'm able to come right up against that disaster without falling into it. Well, I say I am.
And because for each finite fragment, you have to skirt it in a slightly different way every time. And somehow that's your point. It's just not sort of handed down on high.
Yeah.
To do it. It's
Yeah.
a little bit of extra creativity each time, so to speak.
Yeah, because you look at this and you might, if you know the compactness theorem, you say, wait a minute, if every finite fragment is consistent, then the whole thing is consistent. But precisely because you need different skirtings for different fragments, you can't make that step. And this isn't something that in embarrassment we had to say, hey, let's add this extra rule. No, it was already there. So we really were able to come this close, and a genuine obstacle protected us from going farther.
So is this extra bit of creativity, so you're saying in practice, for any finite fragment, you can prove consistency. It's not like there's a theorem which says for a finite fragment.
There is a theorem, but you might know more about the way I would put it. It's not a uniform proof. You don't actually prove for every finite fragment. For each finite fragment, you prove that for each finite fragment there is an argument that will suffice, but there isn't one. Yeah.
Okay, thank you.
Yeah. And precisely because this is good to talk about. It's precisely because you might think something like this won't happen. You might think, hey, this is a consistency proof, but it does happen, and it's not. So as far as what I want, I'm not saying every mathematician should each moment ask what axioms are using. Actually, Harvey Friedman has conjectured that perhaps in the not too distant future, this will actually be a requirement in math journals. You won't be able to publish an article if you are not able to say which axioms you used for your result and furthermore prove you needed to use them. Or to reverse that result to show you that your theorem actually implies those axioms over some base. And Harvey makes a nice point. Harvey says you might think we have 3,000 years of mathematics behind us, but we really only have a couple hundred years of very many people very actively pursuing it. There's only isolated periods in that 3,000 when there's any community actually pursuing it. So we don't know what math will look like in 1,000 years. So he thinks maybe he does. Yeah, I don't know. But that's not what I'm saying. I'm not saying that. Does anyone worry about the foundations of this building? And of course, the answer is yes. A lot of people have and do, so we don't have to. Not everybody has to, because some people do. This is the problem with things like the mathematicians' liberation movement, as I understand it. Maybe I'm being unfair to it. You don't want to get too happy about the irrelevance of foundations. Read Sophus Lee, read Felix Klein, read Paul Gauguin in the 19th century. I mean, really, read them. Read 1920s algebraic geometry or differential geometry. And I'm not kidding, these are beautiful. They're worth reading. And they are hard. They are madly hard. You can't tell what's a given, what's a guess, what's a theorem. You can't tell how the definitions of half the terms. You're supposed to already know that. This should give you a sense, if you actually read these people, you will get a sense of how far set theory, Warwick, category theory, and these things have clarified math. Math is substantially easier to learn now than it was 50 years ago, and it was substantially easier 50 years ago than it was 50 years before that. And partly this is because of improved printing technology, making a lot more books available, but it's also because of foundations. Because in the early 20th century, people adopt set theoretic foundations, and this means they put everything into a uniform framework. The books do not start quoting axioms of set theory, for the most part, although some do. What they do start doing, there become uniform standards of what's a definition, and once there's uniform standards of what's a definition, you start getting more uniform definitions. There are uniform standards of what's a reliable inference. Math journals today contain far fewer mistakes per page than math journals did in 1880. In 1880, it made sense to talk about mistakes per page. Today, we might talk about mistakes per article. The foundations are worth understanding. I will say this, so then in terms of incompleteness, there's prima facie two kinds of incompleteness. Now we're getting more towards the stated, the title topic of the talk. We distinguish the Gödel phenomenon. There is an accent over that. Oh, it's the wrong one. It's just as Korean and loud. I don't know how it became that. The Gödel phenomenon, which is inevitable in comprehensive foundations. Gödel showed this. Any foundation that's plausibly comprehensive for mathematics will fail to prove its own consistency, and thus will fail to prove some things it can state. And who knows what things it can state. The incompleteness results that arrive directly from that are generally remote from practical questions. They're not things that really come up that often. Contrast that to concrete incompleteness. For example, Zermelo-Frankel doesn't prove the axiom of choice or refute it, either one. So if you know Zermelo-Frankel, you still have to wonder about the axiom of choice. And then once you know axiom of choice, you still have to wonder about the continual hypothesis. PA doesn't prove this, the Goodstein theorem or Paris-Harrington's Ramsey theorem. These are sort of specific things. So with Zermelo-Frankel, we had the axiom of choice as an axiom. Almost everybody, we now call it ZFC, almost everybody takes the axiom of choice as an axiom. Almost nobody takes the continual hypothesis as an axiom because it's not of very much interest to most people. Do we take the Ramsey theorem as a new axiom for arithmetic? I've never heard of anyone doing that because the need isn't there. People don't care that much what's in Pan arithmetic. It's all provable in Zermelo-Frankel or any other set theory. Is concrete incompleteness inevitable? Could you have a theory that maybe it doesn't answer all the meta-theoretic questions like its own consistency, but it answers all the concrete questions that you wanted to know from it? I think this is not a clear-cut question right now. In other words, is this a true dichotomy? Is there really a difference between Gödel phenomenon and concrete incompleteness?
So you don't think Harvey's Boolean relation theory they're sort of concocted, but it is very concrete once you actually look at this example.
Oh yeah, I don't think this is a bogus distinction. I think it's an important distinction in the current state of knowledge. To try to find concrete incompleteness should be mathematically meaningful statements that are independent of their axioms.
Well, rank and file mathematicians already cared about.
Yeah.
So not formalized, that's a sociological,
Yeah, yeah, and there's certainly a clear distinction between the Gödel sentence and the kind of question that rank and file mathematicians routinely care about. But is it a true dichotomy? Are we actually going to be able to split all independences into either this or else that? Or are we at least going to be able to draw a clear line? Maybe they will run up against each other. I don't think we currently know enough about concrete incompleteness, really, or Gödel incompleteness to know, is this really a dichotomy or not?
But isn't the consistency of PA the concrete incompleteness that is also a Gödel incompleteness?
Well, but as a sociological matter, you go to a math department, lots of people are willing to say, I don't care about the Gödel sentence.
But the consistency of PA was worried about before Gödel.
By Hilbert, yeah.
So it should count as a concrete incompleteness.
Yeah. I mean, it won't do to say mathematicians don't care about these questions, because then you're claiming that Poincaré and Hilbert, for example, weren't mathematicians. But there is still a difference between the reasons for caring. Right now, people are always trying to find more and more natural statements in Peano arithmetic that will be independent of it. Harvey's Boolean relations, he wishes he had simpler, more natural statements that were independent of weaker axioms. So I think this is a good prima facie distinction, but I do think it's an interesting question. How firm is it? And I'll get to that. Concrete incompleteness is not entirely inevitable. That's certain. There are important complete theories. Tame theories, minimal theories. The theory of algebraically closed fields is complete. You can give first order axioms for algebraically closed fields that answer all the questions they raise. Any statement, any sentence in that theory is either a theorem or the negation of a theorem. This decides everything. But this will be algebraically closed fields in which you cannot identify the integers. It's very important that this is a theory in which you can't identify the integers. You can identify 1, because 1 is right there in the axioms. You know 2, because that's 1 plus 1. But you can't pick out the set of all integers. That's what keeps it tame. Minimal theories are a kind of these. Many genuine problems, as in algebraic number theory, geometry, can be put in context free of the Gödel phenomenon, which technically, for shorthand, means you can't define the integers. So you can't start talking about arithmetic there. That is, contexts which will not themselves support the fearsome complexity of mathematical induction. The induction axiom is terribly complex. You can't interpret it in the theory of a real closed field, or an algebraically closed field. Well, both are complete theories. So there are very nice complete theories. There's important working logic being done on complete theories, but precisely these are theories that don't support that complexity. You don't forget the Gödel phenomenon to do this. You take care to avoid it. You take care that your theory will keep avoiding the Gödel phenomenon. So this is not people who don't care about Gödel's theorem. This is people who deliberately avoid contexts where it's going to kick in. But it's crucial that Gödel's theorem is not particularly about Peano arithmetic. I teach it every year. I teach it for Peano arithmetic. But it's crucial that it's not just for Peano arithmetic. Robinson, that B is unfortunate. Raphael Robinson comes up with this arithmetic Q. It's a theory of arithmetic. It's a very weak theory. You have no induction in this. The only induction you have in this is you know that every number is either 0 or a successor, which you can easily prove by induction. Robinson's arithmetic proves very few things. What it does do is it proves Gödel's theorem. Well, it doesn't. I don't know if does it prove it? Anyway, it supports it. Any consistent extension of Robinson arithmetic is incomplete.
So you can do the coding theorem?
I'm not sure about that, but the theorem. But you can say wherever you had to be to give the proof, you can't give a proof that it's incomplete and all its consistent extensions are incomplete. Elementary function arithmetic, EFA, which I'll come back to in a minute. Second order arithmetic, elementary theory of the category of sets, Zermelo, Frankel. The Gödel's theorem applies to all of these things, and it applies to them all equally. EFA, you can give the proof in EFA. And I want to point this at one way to challenge the distinction between Gödel incompleteness and concrete incompleteness, the Gödel's incompleteness theorem for pound arithmetic can be understood this way, and if you haven't seen it before, this is maybe not a bad way to understand it. We can ask, let's say sentences of arithmetic that can be stated in less than 105 characters. Harvey has some theorem about the ones that can be stated in less than 37. There's not many. Now there's infinitely many because you can change variable names, but there's essentially only finitely many. I hope you'll believe me, there's essentially only finitely many. So there's only finitely many of these theorems. Each one of these theorems has a proof, has many proofs. Each one has a shortest proof. What's the longest length that occurs as the shortest proof of one of these theorems? We can ask that. Once we know the longest length of the shortest proof of any formula that can be written in less than 105 characters, now you give me a formula in less than 105 and I can decide whether it's a theorem, because I know how far I have to look. I've been told what is the longest that proof could be, so I only have to look for potential proofs up to that length. So Gödel's theorem implies this function cannot be definable in arithmetic. If it was defined in arithmetic, Gödel's theorem will fail. So pound arithmetic cannot prove that this function is well defined. Well, this can't be a recursive function, is actually how Gödel's theorem is often stated. This can't be a recursive function. If it was a recursive function, we'd have a definition of it, and Gödel's theorem would be cheated. So that is Gödel's incompleteness theorem, can be stated that way. The Paris-Harrington incompleteness for pound arithmetic can be stated saying the smallest set solving a certain finite coloring problem has size growing faster. It is a recursive function. You can see it's a recursive function, but it grows faster than any function PA can prove exists. I think I've got that right. It certainly grows faster than any function PA can prove exists. So this is another incomplete. This is commonly considered a concrete incompleteness result, whereas the first is, well, if anything is Gödel phenomenon, I guess Gödel's proof of Gödel's theorem is Gödel phenomenon.
So if you were to take this weaker claim about, provably recursive and replace what you have in verbs, what does that weakening give me? Is that some? I mean, there's this. You're saying there's a difference. So I'm trying to put what is it about Gödel's completeness theorem that we'd be missing out on?
Well, this is how Paris-Harrington actually proved their result. They showed that if you had this function, you could jack it up to the function, this function. So that can't be possible. Pound arithmetic cannot prove the recursiveness of every recursive function. The Paris-Harrington is a recursive function, but not provably recursive. The Gödel result is about something that's not even a recursive function. And then here I state the coloring problem. If you like Ramsey theorems, if you're good at explaining Ramsey theorems, maybe you could talk to me after this. The tetration function, y to the y over 2, I don't even know how that's pronounced. This is 2 to the 2 to the 2, so it is 16. Did I do that right? 2 to the 4th is 16. You do not want to calculate that number. A computer, it's not a big number. You can see it's only like 30 digits long or something, but I'm not going to do it here on the board. This function grows faster than any function that elementary function arithmetic can prove exists. Now here we're dealing with something that I don't know, would this count as concrete incompleteness? This function is concretely not provably existent in elementary function arithmetic, but you can see I'm pushing this pattern, and it's the same kind of an argument. So there's incompleteness at all different levels in elementary function arithmetic. What is elementary function arithmetic? It's a concrete arithmetic in Hilbert's sense. Hilbert says this claim is not concrete. This claim is not contextual, inhaltlich. This is to say that every number is n is less than some prime p is not concrete. Why is it not concrete? Here's what would have been concrete. Every number n is less than some prime that's less than n factorial plus 1. This is concrete because now I know how far I have to look to check it. This claim, Hilbert says, this claim gives me an actual problem in calculation that I can do because I know how far I'm going to have to go. The other one I didn't know. Now, the other one, I mean, Euclid's own proof entitles me to that second claim. But Hilbert's making the point about the assertion itself. The assertion wasn't concretely made because it didn't tell you how far you'd have to look. Exponential function arithmetic is an arithmetic that uses just the functions addition, multiplication, exponentiation, well, also successor, of course, and bounds like this. You need to be able to put bounds on all your quantifiers that are expressed by exponentials. And what interests me in elementary function arithmetic, Harvey-Friedman has a conjecture that Fermat's last theorem can be proved in EFA. This is not a conjecture on which we have vast evidence, but I will have to tell you that the more I look at it, the more I think it might be true. It's uncanny. Virtually all the arithmetic we know of, that we know whether or not it can be done in EFA, we know it can. EFA reaches very, very far. You wouldn't know offhand, but it does. So this is, what does it take to prove Fermat's last theorem? Can we do it in EFA? Can we do it in Peano arithmetic? Can we do it in Zermelo-Frankel? Yes. We know you can do it in Zermelo-Frankel because it's been done. Can you do it in finite order arithmetic? We'll take the Peano axioms plus we'll allow sets of numbers and sets of numbers and sets of numbers up to every finite level. Will that suffice? Yes, because you can prove it will. That proof is known. Can it be done in Peano arithmetic? All the smart money says yes. And if you know, when I say that, I think yes. I wouldn't have said that if I didn't think yes. But we don't know. We don't know. Can it be done in elementary function arithmetic? Not known. And this is something that I've gotten actually deeper into my own mind from preparing this talk. Gödel's theorem tells you there's no one level to look at. You see what I mean? If Peano arithmetic was complete, it would be the court of appeal for all consistency questions. But it's not. There is no court of appeal for all consistency questions. There's no one court of appeal for all deducibility questions. If you're going to take foundation seriously, you always have to ask, what does it take to prove this theorem? You know, not that everybody has to all the time, but you always have to know that. There's no one place where everything that should get proved is proved.
So this might just be a clarification point. At one point you were saying that we've not only tried the induction schema for what we mean by sensitive
Oh, I'd say a little more than that. I mean, we've only used it in cases where we knew what we wanted it to do and got it to do that. And nobody was ever trying to get it to prove inconsistency of PA. Unless Ed Nelson has tried that, I don't know.